Hello and welcome to this video lecture. In this lecture, we're going to talk about the numerical integration of first order ODEs. So let's say that we have a differential equation and that differential equation can be solved then of course that means that we have a function which is called the solution that captures the system response. And if we choose to, we can plot that response so that we see how the response evolves over time. Because once we have a function, clearly we can plot it. But let's say that we have a case, and this actually happens probably much more frequently than the first case where we can actually solve the differential equation. Understand that for the vast majority of the problems that you are posed in or given in both your differential equations class and this class, they are very simple problems, somewhat contrived problems that allow you to actually come up with what I call a closed form solution. When you're actually out in industry and you're working to try to figure out what's happening with a particular system response and the differential equation that's associated with that response, quite regularly, you're just not going to be able to solve it. Or if you could solve it, it would just take so long to do that it's just not even worth it. So let's then look at that case where we can't come up with that quote unquote closed form solution. Let's put a U in there, or let's actually just frame it this way. If the differential equation is difficult or impossible to solve, clearly then we don't have or here I'll say can't find a closed form. Now let's just say function, because that implies closed form. That represents the system response. Let's just say response. I think you know it's system. Come on, go away, eraser. And we can see that there are some cases where we really probably wouldn't want to try to find an actual expression for the system response. Now, I'll admit that this wouldn't necessarily give me a single first order differential equation, but you can kind of see when we might not be terribly interested in trying to find a closed form solution if we don't absolutely have to. So maybe we want to find the response of and let's say, just for the fun of it, we'll have a Vn over here. I'm just going to have a single Vn, a single input, though clearly you could imagine that you'd have multiple ones. And I'm not even going to bother to label these. So we might have a resistor, a capacitor, and then let's come on over and have another resistor. And then we'll come down to a capacitor, and then we'll wrap another resistor around in parallel with that capacitor, and then we'll bring all of that back around over here, and then let's, for good measure, throw in another let's go ahead though and give ourselves another lead there. So we'll have another resistor coming in over here, and then let's go ahead and have a capacitor and a resistor, and let's go ahead and have our output, and we'll have another capacitor here just for fun, and we'll go down to a resistor, and then let's have another capacitor, and then let's go ahead, just for the fun of it, let's have a capacitor that just kind of spans across here just for fun. There we go. And you can see that we can just get truly ridiculous. And so this will be our V out. And if I wanted to, hey, yeah, why not? Let's just go ahead and throw in another capacitor and resistor here just for the fun of it. And so you can see that, you know, when we're looking at each of those capacitors, each one is a dynamic element. So in theory, we, of course, could try to find an equation that captures V out given some kind of Vn, and Vn can even be a time varying signal and generally will be a time varying signal as well. But we could see that each capacitor, as I just said, is a dynamic element. Meaning that it has its own dynamic response. Now, for a relatively simple system, and you might think that the one I've drawn up above isn't terribly simple, but actually it is. Yeah, we might be able to get away with it. Get away with coming up with an actual closed form solution. So it probably wouldn't be impossible in this case, whose voltage of course can be changing. Let me spell changing properly though. So the voltages can be changing in time, assuming that we're still, of course, in the, or we're interested in or still in the transient phase of the response. So clearly, if we have voltages that are changing, or they could just be changing because we have a time varying input, which is also another distinct possibility. So even if we have a persistent response that is changing in time, that is certainly a possibility if we have a time changing input. And so we can see that it makes it clearly difficult if not impossible so tying it into what I said before, to find an equation that relates V out to V in terms of the response in time. And here I can say even one that includes one or more integrals. Because of course, to relate the voltage to the current, when we're dealing with a capacitor, we have to integrate that current in order to figure out what's happening with the voltage. So here we would end up with a whole bunch of integrals associated with this particular circuit if we chose a particular way of representing what was happening. So even though we might be able to solve this, and again, I'm kind of looking at the day when you might be out in industry, I think your boss would be a little less than happy if you spent a whole week trying to figure out the closed form solution for this particular type of circuit or this particular circuit. They would be less than impressed, because it turns out that we have easier ways of figuring out what's happening with these kinds of circuits or these kinds of systems. And so that's the tool you would want to use when we start talking about these relatively complex systems. And even this one wouldn't be considered terribly complex, to be honest. So let's capture that this clearly is a significant issue. Because, of course, so here this gives us a little motivation, because most systems will have states that change in time, i.e. they have a dynamic response, and they will clearly change in time if we have a time-changing input, or an input that changes in time as well. I don't know why that arrow got a little messed up. Let me see if I can erase it. And so if we are able to frame things in the appropriate way, we can have integrals, or we can have derivatives. So here we can say that, and I will assume that we have been clever enough to figure out a way to express the governing equation. Here I'll just say equations. That we've been clever enough to express them in a way that they have derivatives. And it's important for us to recognize that most of our fundamental laws generally involve derivatives. Now, clearly we can see that in some cases we deal with integrals, but derivatives are really one of the things that we encounter most frequently. And if we have an integral, we can try to reframe things in a way where we end up with derivatives, because we kind of assume that we're dealing with derivatives rather than with integrals. And you'll see that here in a moment. Now, one of the things that's nice about dealing with engineering systems is we know that we can always say something about a system. Let me go ahead and frame that as, or state that as, because of the real limitations of the system. And here, mechanically, we may have inertias, we may have some dissipation, we may have other things that are happening in the system. And those things will, of course, prevent a system from responding instantaneously to a particular input. It just can't happen. So because of the real limitations of the system, we understand that if we know where it is in the present time, we can say that in the future, it can only take on a limited range of values. So in other words, if we knew that our system was coming in with this kind of trajectory, and we're now at this point, and we're trying to figure out what the next point is, well, we can clearly see that, let's go ahead and go over to this color. Yeah, we'll stay with that. Well, okay, since it did come up. We can clearly see that just a hair over in time, we clearly can't end up here based on the real limitations of the system. We also can't end up way up here. Now, of course, the relative values that I'm discussing here would be associated with what we know about the system. So here I'm just kind of making up points that are pretty far away to give you an understanding that clearly a real system just couldn't jump to those values. And so what do we know? We know that the next set of possible values need to be somewhere in this range. And so, and maybe even these further ones that are further out just aren't adequate as well. But we know that, and this is kind of like the hurricane mapping that you see where things kind of start getting further and further away from what we would consider probably the mean line associated with the system response. But of course, because of changes, yeah, we can certainly see that the system response could diverge further and further from our current value, or move further and further from our current value might be a better way to say it, as we move further out because of the possible changes that are allowable for this system. So these are acceptable. Response values at some particular time out. And of course, the whole point is that these are clearly unacceptable. Let me kind of wrap that around here. And so these are unacceptable. And this in particular, when you're out in industry, here we're talking about a system response, but this can apply to all sorts of different things, such as component dimensions and things like that for a component that you haven't designed yet. It's called bounding the problem. It's saying that if we're designing something, maybe that's the size of a toaster oven, and somebody's asking us to design a knob for that toaster oven, or they want to know the maximum size of the knob for that toaster oven, well, we can probably reasonably say that that knob isn't going to be any bigger because a toaster oven is, maybe about 1.5 by 1.5 by maybe a foot or something along those lines. Relatively reasonable size, maybe up to 2 feet by 2 feet. So, how big is our knob going to be? Are we going to have a knob that is 1 foot in diameter? Of course not. That would make no sense. So you can say, well, if you need a maximum size for that knob, I would say that it probably won't be any bigger than, have a dial that's any bigger than a 2-inch diameter, because it just wouldn't make sense. Not only wouldn't it make sense for us grabbing onto it as human beings, which is why most of our knobs are, generally in the same range of sizes, but it also wouldn't make sense for the size of the device that you're designing, because this huge knob just wouldn't match what you're trying to do and wouldn't even actually fit on the toaster oven itself. And so that's called bounding the problem. You haven't designed the knob yet, but you can say something. And that's exactly what I'm saying here, is we can say the same thing about a system response, knowing the inertias, knowing the dissipators of energy, how the system dissipates energy and things like that. We can say something about the system response without actually knowing exactly what's happening with the system. Fortunately for us, though, if we're able to write the governing equation, i.e. the governing differential equation for this system, we can do something even more. So let's go ahead and capture that discussion, this idea of bounding a problem, which is absolutely crucial. And understand, that's what happened to me when I first got into industry. Almost one of the very first things that somebody did, so I got assigned to a design project. And one of the folks that was going to be interfacing with my particular system said, we need to know something about that system. And of course, being a new grad engineer, I was like, well, I can't tell you anything because I haven't designed it. And they kind of looked at me funny, and not necessarily a pleasant, funny way. And they're like, great, glad you can't say something specific. We want you to bound the problem. Go bound it. Tell us what's going on. Just give us some idea. And so then I went off into that exercise of, okay, well, clearly I'm dealing with something this big and it's going to have this mass, roughly this mass associated with it. So my interface will have to do X, Y, and Z. The interface on my side, and of course, whatever is happening on the interface with my side, that's going to affect the interface on their side. And so it turned out it wasn't terribly difficult to do, and it's something that you'll probably be exposed to before you're actually finished with your first design. So make sure that you kind of take this discussion to heart here, because this is a skill that most students, most engineering students aren't taught before they leave. I certainly wasn't. And it's something that was absolutely crucial when I got out into industry, because that was almost the first thing I was asked to do, was just start bounding at the outset of my first project, before I was able to design anything. And so that was kind of the first skill I had to really refine when I got out into industry. So with that, let's go ahead and capture this part of the discussion. So clearly, the point that I'm getting at here is that we can clearly say something, because the system isn't a complete unknown to us. We can say something about the next value. Even if the system isn't completely defined for us, we can say something about that next value. Because we know it can't be infinitely high on, or infinitely far up on the upside, or infinitely far down on the downward side. Just can't happen. Real systems can't support that. So we can say something about the next value of the system output as time marches on. For us, it would be in the next time step for what I've indicated here. Now, here, though, I don't want to necessarily get into a discussion of exactly how we would bound the system, because I'm going to assume that even though we can't solve the differential equation, we can at least write the governing differential equation for the system. So one of the statements, so here we can say something, maybe we don't even know precisely what's going on with the system, but we know roughly what's happening. But we can make an even better statement if we know the system, and we know the governing differential equation for the system. Then we can really start to say something precise about what's going to happen with the system response in time. So here, I'll say that the statement of what the system will do is captured by its governing equation. So that means that if we can somehow, so remember, we have these derivatives associated with the governing equation. So if we can somehow integrate and here I'll bring in the idea that we're going to be doing this numerically. Let's say this governing equation. Be good. And here I'll shorten down governing and equation. We can, and I'll refer back up to this figure here in a moment, we can estimate the near-term value of the response. And here I'll spell out response. And we can do that based on the present value, because we need to know where the system is. Otherwise, that would be pretty much impossible. If we didn't even know the current value of the system, how could we figure out what the future value would be? And again, the governing differential equation and we can do that without actually knowing the function, and there may not even be a function, knowing the function that captures the system response. So how do we do that? And we'll see that here shortly in the mathematics. But you can see how we might approach it. We have a governing differential equation. So when we talk about a differential equation, we know something about, remember, differential derivative, we know something about the slope of what's happening with, so we don't know the underlying function for the system response, but we know something about that function's slope because we've captured it in the differential equation. And so we can then use, and so here we can say that we are extrapolating into the future let's put a using in there first. Using so here I'm going to recapture these two bullets because we're going to bring in the idea of the derivative here in a moment. What we currently know need to get my K in there. What we currently know about the system response, i.e. its present value, and what we know about how the system will respond. To kind of put these two things into a bit more of an understandable statement and how the system will respond. Based again on that governing equation. Okay, so that's another way to say what we're going to be dealing with. And so let's go ahead and introduce, and there are many methods. We're going to introduce probably the simplest method. So we can use what's called Euler's method to do exactly that. To go from our present value of the response to a future value of the response using the governing differential equation, provided we can write it in a particular form. And then this will harken back to one of the things that I mentioned right at the very beginning of this discussion. So provided that the governing equation can be written in the following form. So remember how I said that this will work for equations that can be written as first order ODEs. So here we'll assume that the system response is y, and we're able to write the governing differential equation as dy dt, where y again is the system response, I'll capture that in the notes in a moment, is equal to some function of our independent variable t and the actual system response itself, y. So that's pretty nice. We can actually deal with something that is quite likely a nonlinear differential equation. So we can approach solving these very difficult equations, potentially very difficult equations. Oh, don't know quite why things were moving there. Using this Euler's method. Now, again, Euler's method is a fairly simple method, one that I wouldn't necessarily recommend in most cases. There are substantially better methods, but the key with Euler's method is that it's conceptually the simplest one to work with initially. So let's capture what this equation says. So remember how I said we're going to be dealing with the derivative and the slope. Well, there it is. And so notice, if you go back up here, I did something a little intentional. Notice how for these 3 points, I kind of biased them on the upward side of our current point. And why would I do that? Because look at, you can clearly, whoa, let me kind of undo that if I can. Come on, be good. Let's see, Control Z, Control Z, Control Z. That didn't work out well. Control Y. Oh well. So hopefully it restored it. Well, we got something over here, so that's good. Let me make sure I'm on my pen again. So notice that I bias these upward because clearly the slope at my current point has a positive value associated with it. So the realistic values are all going to be biased upward just by virtue of the slope that I'm dealing with. So let's go ahead and so let's capture first order differential equation. As I indicated right at the beginning, that's what we will be dealing with. Now here, we have to represent it explicitly as a first order differential equation. If we have higher order differential equations, we can manipulate those differential equations into a form that captures the same behaviors as first order, actually a simultaneous set of first order differential equations. But with that said, let's just go ahead and assume that we just ended up with a first order differential equation once we wrote down the governing equations for the system. And so this says, and we will be using the derivative and the slope to determine the value of the next point in time, that the derivative of the dependent variable y, which again represents the response that we're interested in from the system, it says that that derivative is a function of y and the independent and let me get an I in there, independent variable t only. So when we're looking at this, we can see that if I know t, well, first of all, if I know that function, and I'm assuming that based on our differential equation, I was able to work with or get the function, or get the equation would be a better way to say it, get the equation in this form. And so that says that if I know the value of the system response at a particular time, t, I can just plug in that particular system response and that particular time, and I now have the slope of the underlying response curve at that particular time. So here we can capture that as we must evaluate. So clearly we must be able to do that. So that function must be able to be evaluated clearly at specific values of y and t in order to make this work. So that means that we can't have integrals floating around in this expression. So when we're looking at function of t and y, we can't have integrals, we can't have other derivatives, as is indicated since this is a first order differential equation, but we can't have other derivatives floating around either. So we have to be able to get it into that particular form. So now going ahead and realizing that dy dt is simply the slope of the response curve, and we now know that we can find it. We can find that slope even though we may not know the response curve itself. And here I'm capturing that Y is the response that we're interested in. And so what does that mean? That means that that slope gives us the direction of the system response at the current state. And since these systems can't just change dramatically, then as long as we go ahead and estimate the system response just a little bit in the future based off of this slope, we can then say, okay, this is going to be the next point on the system response, or the next pretty good estimate might be a better way to say it, the next pretty good estimate. And so this can be used to find an estimate of a future point on the system's response. Because of course, the underlying response curve isn't going to diverge much from the slope over a very, very short period of time. Now, of course, if we start jumping too far into the future, that slope won't be representative of what's happening with the system response anymore at those points far in the future. And so, of course, then we have an issue. But provided we go with relatively small changes in time to propagate the system response forward in time, then it really isn't an issue. So we can use this slope to find a future point or the response at a future point in time by saying that yi plus 1. So we're going to assume that right now we're at yi, so we know what yi is, and we're going to find a future point. We'll call that next point yi plus 1 is equal to, well, what do? I just need to figure out what the slope is at this particular point in time and at this particular value of the response. And then I just need to propagate that slope over some period of time. Ti plus 1. So Ti plus 1 will be the new point in time that we're trying to propagate to. Ti will be the point that we know right now. And of course, what's the slope? The slope, and I'll write this down in a moment, but the slope is just rise over run. And so if this is my run and I multiply it by rise over run, then you can clearly see that this product is just going to give me the rise, i.e. the change in y, since we're plotting y on the vertical axis, will just give me that change in y over that period of time. And I just add that onto my current value of y, and then that will give me my next value of y. So let's go ahead and capture some of this. So we have our now, we have our future, we have our time, we have our response, And here I'll go ahead and shorten down response, where of course response is y. And so just to put these definitions in a table, just to make things a little bit easier, our present time is ti, our present response is yi, both of those are assumed to be known. Our future time is ti plus 1. The future value of our response is yi plus 1. And of course, that yi plus 1 corresponds to that ti plus 1. So here, capturing conceptually what is going on, f ti comma yi is just the slope, i.e. rise or delta y, over run delta t, where delta y, of course, would just simply be yi plus 1 minus yi, and run would just be ti plus 1 minus ti. And so, and if you plugged that in right back up here, you would see that suddenly we would get yi plus 1 is equal to yi plus 1. Makes perfect sense, right? So it's just the slope of the response. And here I'll continue to say curve to just emphasize that we're trying to figure out how that response is changing or propagating through time. And then, of course, that ti plus 1 minus ti is the period of time we are extrapolating, or propagating is usually the term used, across. So conceptually, we can see exactly what we're doing. We have a differential equation where the derivative gives us the slope of the unknown but desired response curve. So we go ahead, we solve for that derivative so that we can get that slope. And once we have that slope, we can use that slope to find a point in time, not far away from our current point, but a point in time that will give us a future value in the very near future, the future value of the system response. Now, what happens if I want to go further? Well, if I want to go further out, what can we do? Well, we can just go ahead and repeat that process, which is why I was using i's rather than ones and twos and things like that. So we can continue to repeat that process. So once I get that next point in the near future, I now have the system response and I have a time. And so now I can go and plug those right back into this, quote unquote, plug that right back into this very same equation, which is captured by this function. So I can just plug those values into that function. And there we go. We have now a slope at that new point. And then we can use that slope to figure out the next point in the near future. And then the next, and then keep repeating that process, the next point, the next point, the next point. And we can propagate that response trajectory, if you want to call it that response trajectory through time to figure out how the system response will evolve over time without ever having to solve the differential equation, which again could either be difficult or impossible to do. And you can see that for very complicated systems, what could I do? I could just have, as I indicated before, a set of simultaneous first-order differential equations, and then I just work through propagating all of those through time for a very complicated system. In particular, that can be considered what we generally call a state space approach, where we have a simultaneous set of first-order differential equations. So, but not really going to get into that in this class, but I just want to put it out there so that you can understand how this process can be used. Now, one thing that I want to mention, or well, that I mentioned, but I want to get in your notes, is just slope, and then we can just go ahead and extrapolate across. Let's actually move that indentation out a little bit further. Come on, be good, go away. For some reason, my erasers decided to stop working. So this process can be repeated iteratively to determine the system response over, at least conceptually, over an arbitrarily long period. Oops, let me get my eye in there. Now my eraser's over functioning. Of time. Now, of course, and I'll get this in your notes in just a second, or in the notes in just a second, clearly the closer we are to a particular known point for the state, the estimate of the response will generally be better. As we start to get further from that point, that known point, clearly errors are going to creep in, because each time we are extrapolating, we're not getting a perfect representation of the system response itself. And so each time we're doing that, we're getting an estimate, and then the next one we're getting an estimate on top of an estimate, and then the next point an estimate on top of an estimate on top of an estimate. And so you can see that there are two things going on. One is that we can get, and this method, Euler's method, is susceptible to error propagation. So we can develop and accumulate error as we continue to use the method. And because each point starts getting, starts having error on top of error on top of error, we want to minimize, if we can, the amount of time or the duration of time that we're integrating over. Now, sometimes it can't be avoided, but it can happen. So if you have an opportunity to predict the system response to some point in time, and you start understanding that you might start getting relatively large errors, then maybe it's possible to check back in with that system at that time or earlier, so that you can get a known system state again, and then restart your propagation from that point. Now, in a lot of cases that can't happen, because you're trying to design something and this is all happening in a virtual world. You don't have a real system to check in with. But for my experience in industry, we did. So we would have a vehicle on orbit. We would do an orbit determination. We would go through an orbit determination process for one particular point in the orbit, and then we would propagate the orbit from that known point. And based on our understanding of how reliable our propagation approach was, our propagation methodology was, we would understand that we're starting to get some errors creeping in, and so then we need to go and repeat that process of that orbit determination process again within X period of time, or T, let's say T period of time, to ensure that we could continue to propagate that orbit properly. And so in that particular case, we were able to say, okay, we'll check in here, understand what the system is doing, what that vehicle is doing, we'll propagate it, seeing how the errors are kind of creeping in. Then we'll say, okay, now the error might be getting a little too large, so then we'll go ahead and do that orbit determination process. Maybe just, I'm going to arbitrarily say 4 days. So we would understand within 4 days that we would start accumulating too much error in our propagated trajectory. And so then we would check in on day 3 rather than day 4. And then we would reset everything and then start propagating again. And we would just continue to check what that particular vehicle was doing within the appropriate time frame, or within an appropriate time frame, to make sure that we could effectively reset our errors back to 0 and then start propagating again. So that's something that you may want to consider. But again, if this is all in the virtual world, you're trying to figure out what a some kind of motorcycle might do based on some kind of input, like it's going over a rough road of some kind, and this is all being done virtually, there's no way for you to check in and see what's happening with the real solution. So, so understand that in some cases you can check back in with the system and reset whatever error propagation issues you're having. Other times you can't. So process can be repeated iteratively to determine the system response over however long, at least in theory. I'll put in parentheses, best to propagate over short periods of time, if you can. To minimize, I guess I don't need a comma there, but of course my eraser's getting funky on me, so to minimize accumulated error, additionally, and here I'll just say, because, oh, already thinking of the U, need to get the E in there first. Why is my eraser being so problematic? My apologies. And I also don't know why I keep getting this little kind of sticky thing going on with the lines too. Because this method is, well, let's just say has trouble. With error propagation. Additionally, One way, so a couple ways that we can fight this. One is not to use Euler's method, because again, Euler's method is probably the method that is most susceptible to this error propagation, or one of the methods that's most susceptible to error propagation. So we can use different methods that thankfully do a better job of estimating what's going to happen with the future points. One method is called Yoon's method, and what Yoon's method does is it goes ahead and propagates forward, just like Euler's method, propagates forward to the end of the time step. But instead of using that value, Yoon's method then uses that point to calculate the slope, an estimated slope at the end of that time interval. And then, because that slope is going to be ever so slightly different than the slope at the beginning, then Yoon's method uses both slopes simply by taking the average of the two, and it applies the average estimated slope across the time interval rather than using just the single slope at the beginning of the time interval. And so then it goes back to the known time and known state, and then uses the average estimated slope to propagate across, just like Euler's does, except it's using the average. Yoon's method uses the average rather than just the one slope, the one estimated value of the slope itself. Because Yoon's method can capture two different slopes, i.e. the change in slope, you're actually starting to bring in an estimation of the curvature, i.e. the second derivative, associated with the propagation rather than just the first derivative. So clearly Yoon's method is going to be a little bit better. And you can keep going with this and keep going with this idea and going with this idea and going with this idea. And probably one of the methods that's considered, I'd say, the standard for numerical integration is a Runge-Kutta fourth order integration scheme. And so that one captures the first derivative, the second derivative, and keeps going up and up and up. And so, and if memory serves, I think it actually does try to estimate up to effectively the fourth derivative. And so that gives you a much better estimate of where things are going to go in time. With that said, if you don't want to go to, and to be honest, there's almost no reason not to use a Runge-Kutta fourth order, because it is a much more capable estimation and it really doesn't cost much more computationally. But nonetheless, conceptually, it is considerably more interesting to work with, and so that's why I'm not going to work with it in this lecture or even in this class. So with that said, with Euler's method, though, if we stick with that particular, this particular very simple method, another way that we can refine our estimate is to use that first derivative over a shorter period of time. And so instead of going to more capable techniques or more capable methodologies, we could instead just say, fine, I'm just going to go with really small time steps. And I'm also not going to propagate too far in the future, right? This is don't propagate too far into the future. That's what that one is. But you can also go ahead and minimize the error by using very small time steps. Now that, of course, is computationally intensive, but if that's all you have at your disposal is Euler's method, or whatever other method you're dealing with, of course, the smaller time step you work with, the better off you're going to be. You can go ahead and take that approach to minimizing the error. So because this method has trouble with error propagation, you can use small time steps. to minimize the error associated with each computation. And here for computation, let's say interval. I like interval better because there are a lot of things going on. So with each interval would be a more precise way of saying it. So we can see some of the limitations associated with this method, that clearly we're getting an estimated response, and in order to make sure that estimate is really good, we need to compute a lot of different points, which back in the day when people didn't have computers was kind of obnoxious, because literally you would have a bunch of people sitting down and doing these numerical propagations by hand, if you can imagine that. Thankfully, what do we have these days? We have computers, and so and very capable computers, and so throwing many small time steps at a particular numerical integration, a particular propagation, actually really isn't that hard to do these days. And these computers, our modern computers are so fast, you may have to blink your eyes twice rather than once before you get the system response, even going up an order of magnitude for the number of points that you use, number of integration points that you use for a particular propagation. Again, assuming a small and very simple system like these systems. Of course, if you deal with a very complicated system with many simultaneous differential equations and things like that, completely different story at that point. But for a very simple system, it's almost irrelevant. Well, I wouldn't say almost. It's close to irrelevant. The size of the time step when we're talking about getting into very small time steps. So the price we pay is we have an approximate response curve. The wonderful thing that we get for that estimated response curve is we can effectively integrate any first order ODE where the side that doesn't have the derivative on it is able to be evaluated. That's it. If you can evaluate, in our case, that was the right-hand side. If you can evaluate the right-hand side, you can numerically integrate that particular differential equation, which is a pretty nice thing to do, because again, there are many more cases where you won't be able to solve a differential equation in closed form than you will actually be able to solve it in closed form. So that's, of course, where this approach comes in, and where the other numerical methods also come in. So with that, we'll go ahead and call this video lecture a wrap, and I will have another set of videos covering a particular example for Euler's method. So again, with that, we'll call this lecture a wrap.